Welcome back, everybody. How did that work out? Did your algorithm work on the different type of maze? Did it break completely? Did it still somewhat work, even though maybe it was doing unnecessary things, namely moving around to get more information when really you had all the information to start with? Chances are that in order to implement an algorithm to solve this new maze, you will have to go and modify your existing algorithm. But that's the key thing here. You will only have to go and modify it. You don't have to start again from scratch because you've gotten all this experience developing an algorithm for the different maze, and now you can apply this in this similar but slightly different context where you're also solving mazes, but you have access to all the information. You see the entire maze before you start. And in particular, of course, that means that you don't have to do the part where you're moving around and you're shining your light in different directions because you have all the information to start with. So you can immediately start planning where do you want to go, what is the route you want to take from where the spaceship is now to Earth. And in that respect, it is similar to parts of what your algorithm did in the other maze, because after you acquired the information there, you were also, to some extent, planning the route. And of course, this might have been not happened in a very sophisticated fashion if you had developed a simple algorithm. So for example, you're essentially randomly moving around, and whenever you have a choice, you go wherever you think is closer to the exit. And that's perfectly fine. But this part you can essentially take and apply in this context here as well. And the main point of this exercise here is really to give you an idea of a very important concept in computer science and, well, science beyond really, but in particular in programming, and that's modularity and abstraction. We can take an algorithm and we can break it down into different parts. This is the part where I'm moving. This is the part where I'm looking around. This is the part where I'm planning the path from where I am to where I want to be. And depending on how well you separate these, you might be able to, in a context like this, where you want to solve a similar problem, also mazes, but slightly different, you have access to all the information, you might be able to take one of those modules, namely the one where you're planning how to move from A to B, given that you now have all the information along the path, so you know where all the walls are and where you can move, and you can just plug that in to a new algorithm that will then be able to efficiently solve this new type of maze. And this is a very powerful concept because it really allows you to avoid repeated work and leverage what you've done in the past. And this is essentially how big software projects happen, how big computer science projects happen. If you're implementing a new version of Microsoft Office, for example, you're not going to just start from scratch. Of course, you have the previous version, but in addition to that, you have all these modular components that you have previously combined in novel and interesting ways to build a new piece of software, and where you can now say that, well, okay, this component is fine and I don't need to do anything here. But here, I just want to change the component itself. And that, because the software is using the component, will automatically improve the software. But any other software that uses the same component will also be improved. So this is a very powerful and ubiquitous concept, and definitely something that you should keep in mind when you're developing algorithms, and then, of course, when you're implementing this as well. If you've done any amount of programming at all, you will have already done this because you will have used what's called library functions. So these are functions provided by whatever programming environment you're using to do common tasks, like sorting, for example, or like activating an LED on your microbit or something like this. So all you have to do is call this function that somebody else has implemented somewhere, and the action you want to happen happens. And you don't have to worry about, well, what does this do internally? How do I actually control the LED? Do I have to, where does the voltage go? How do I actually make that happen? All of that is hidden from you. It's abstracted out in the library that you're using in this modular component that you can just take and use in a particular fashion that might be suitable for whatever you want to deal with. And as I said before, if now somebody goes and improves the implementation of this library, for example, there's a new version of a microbit and you need to change something to support on the LEDs there. They can do that, and you can use your existing code with the new version of the microbit without having to change anything just by plugging in this different module, this new version of the library. So very powerful concept. And again, you can keep that in mind when you're developing your algorithms and when you're implementing your programs. In this particular case here, as I said, one obvious distinction you could make is that you're saying, well, here's the part where I'm looking around for more information, and that might involve moving, that might involve just shining your light, depending on how you implement this. And here's the part where, based on the information that I have acquired, I then make the decision where to move and how to move. And then you could simply, for this new maze, say, well, this first part where I acquire the information, that's no longer relevant. I don't need that anymore because I already have all the information, so I only need the second part. But I can use this second part as is because, well, I just give it the information that I've acquired in a different way by just looking at the maze, and off it goes. Of course, in practice, this modularity tends to increase complexity a little bit because now you need to decide how to communicate information between those two different parts, right? If everything is in one, if you have the looking around and the moving part without any distinction between them, then you don't have to worry about, well, okay, how do I represent that the wall is here and there's a space where I can move? It's just implicit. If you want to separate those, you have to think about this. And you might have to introduce data structures to hold that information and some additional code and some additional steps in your algorithm to create these data structures, to move them around and then to work with them. But as I said, the advantage is really that then you can take these individual modules, these individual parts of your algorithms, and swap them out as needed to, for example, do different kinds of mazes, or even use somebody else's code. Somebody else has developed a really great way of looking around, really efficient, gets you lots of information, much better than what you're doing. If you're anything like me, then that's going to happen a lot. You're going to implement something and then find that, oh, actually somebody else has done that in a much better way already. You can just take that module and plug that in, and that should hopefully be very easy. All right, that's it. I hope you had some fun while you were doing this, and I hope that you have now a better understanding of what's involved in developing algorithms, and in particular making algorithms robust so that you can use them in the real world and give them to other people to use, which, as I hope you have a glimpse of by now, is not entirely straightforward. It can be quite difficult, and that's one of the reasons why, unfortunately, as I talked about before, there's so much crap software in practice. Now you don't have to do this. Now you know how to make your algorithm robust, think about what might happen. You can write great software from now on. Thanks for watching.